All right, so you may or may not be interested in the website, or the not the website, but the you may or may not be interested in the project that we've been doing with the Rubik's Cube. But in high school students in the greater Toledo area, we basically have 387 of the trainers out into the out in the area. Okay, so there's 387 high school students or thereabouts working on the same thing that you're working on, which is basically a combination of labs that are fairly simple, and then they're being asked to program a solution to the Rubik's Cube, which is not simple. And that's a very hard project. I don't know how many of them are going to get it, but that's an interesting project in that that's an NSF grant that we got, and we were determined to see how far we could go with it. And right now there are potentially at least 387 high school students working on their own trainers doing these projects. Okay, the other thing I want to talk about is the syllabus, just real quickly, and there seem to be questions about it, and I want to go over it really quickly again. The syllabus, basically what it says, and that is concerning the points and how they're divvied out, that type of thing. There's two statements in the syllabus. So really three. Lab 2.1 is required, and it's a 2-point lab. It's a simple lab. A lot of you have done it, some of you haven't, but you have to do it on its own. It's 2-point lab. You can do it as a group. I'm not so concerned about if you do it in a single or a group, but you have to do that and turn that in. And you must have 20 points prior to April 1. Now, I'll extend that a day or two, but I'm not going to extend it past the 5th, okay? So if you say, I haven't gotten anything in until the 5th or the 6th, if it's the 6th, it's too late. If it's the 5th, I'll probably still take it. In that range, it's going to be, there will be a cutoff, and it will be a little bit after the 1st, but it will not be by more than 3 or 4 or 5 days in that range. So if you're counting on me giving you another 10 days, don't. Okay, maybe 2 or 3, maybe 4, but not more than 5. Okay, this is going to be it. The other thing is half the labs must be from 8.2 or higher. So those are the two statements that I'm going to hold you to. And also this fact that some of the labs that are in the early stages also show up in Chapter 15, and you can't do them twice. In other words, you can't do the Chapter 15 lab if you did the Chapter 7 labs with the simulation. In other words, the whole idea of Chapter 15 is learn how to do the HMI, and you can do some of the labs that were in Chapter 7 in Chapter 15, but you can't do them both places if you did Chapter 7 with simulation. Does that make sense? You can double dip if you did the wiring on Chapter 7, but if you did the simulation in Chapter 7, you can't go back and do them again. Simple. And the other request I would have, and this is just a request, it's not a firm anything in the syllabus, but if you're handing in a lab on a particular subject and you do the Allen Bradley and the Siemens, please hand them both in at the same time in the same packet, so that I don't have to go back and ask you, well, did you already do, if you hand one in and then 3 weeks later you hand in the other one, or you hand in the same one again, but say it's the other one. I know the difference, but anyway, I keep them in the same, I'm giving you how I do my scoring. I'm keeping them in the same column, and I don't have a separate column for Siemens and Allen Bradley for each one, but I try to keep it separate. I do keep them separate, but on the other hand, please hand them in at the same time. If you do them at the same time, please hand them in at the same time. It helps me tremendously. And if you don't see, when you get handed back, if you hand in both Allen Bradley and Siemens, if you don't say 2 over 2 and 2 over 2, if you don't see that twice, you didn't get credit for both of them, you only got credit for one of them. I missed one. So if you hand them in and then you get back the score and you only see 1, 2 out of 2, you only got credit for one or the other. make sure on your title page you say Allen Bradley and Siemens if you want credit for both. And that's just fair. And I'll go through and look and see if you did both. But on the other hand, when I'm looking at that first page and trying to get a score, I would appreciate you saying both. Okay?
So 20 before 8.2, or do you like as many have before 8.2 as you do after?
You can do labs anywhere, but I will not take more than 20 points before 8.2. You may do labs anywhere. You don't have to do 20 points before 8.2, but you only get 20 points before 8.2. Those are the simple labs. Those are the ones that if you really figured this out, you can go over to the Rubik's project and they're given. Did you realize that? They're all printed out for you. All you got to do is type them in and get them credit for them. They're there. They're there in spades. Most of them, not all of them, but when I built the Rubik's thing, I had to basically go with the high school students. I had to give them something. And what I gave them was some of the simple labs at the beginning. So they're only there in Siemens, and you can even get a 4-point lab in chapter 11 by doing 13 by doing the Simon Says, because it's printed out for you. All you got to do is type it in and get it to work, and then you got a 4-point lab. It's there. It's all, that's lab 6 from the Rubik's project, or week 6 from the Rubik's project. Also, if you are so inclined, if you look at the beginning of the Rubik's project, okay, let's look at the Rubik's project for a minute. Okay, so here is the high school Rubik's. And I don't think anybody's done anything with that blog. I'm going to probably take that out, so that will be gone. But down here under text accompanying weekly projects, okay, this is a slightly updated version of this book, or whatever you want to call it. And here are all the early helps that have to do with the getting things set up. And again, if you're interested in the some of this stuff is version 20 stuff, version 19 and version 20. But one of you came, Tyler, is he there tonight? Tyler Blue? Okay, here is what we were lacking the other day. And this is what I had to get an administrative rights to do, but we did this yesterday and it worked. So that processor now works. So here are some of the fixes that get you so you can do simulation. Version 16 works. Version 20 has a lot of complications because they added a lot of things to version 19 and version 20. And you're fortunate that you're still under version 16, but 2 of our computers down there are version 20 computers, and they have all this stuff in them. And these are just things that you need to do and need to check off if you have a problem. But this was the one that was still missing right here, this one. And this is stuff that we have to hand to the people that are out in the high schools, and they're using version 19 and version 20. And this is the one, this is page 22 of the that text. So that is what we were missing the other day. So if anybody wonders what I do with my extra time, it's troubleshoot version 20, among other things. This is one of the problems that Tyler found the other day. No, I had found it earlier, but then I did not have administrative right access, and I got someone to help me, and we went through and did this change, and it worked. So that was that one. After you do this, after you make this change, you have to go back and recompile everything and download to the PLC, and then it will work. So you do this change, recompile the world, and then it will work. So that's that. Okay, I want to get back to chapter 19. And in this chapter, there's several things going on. And one of them is this whole idea of building a drawing called a P&ID, okay? So we talk about PID, which is the algorithm itself, and then there's a drawing that goes along with it called a P&ID. Sorry. So the two they're not the same. The PID algorithm, and I've got to change my font. The PID is the proportional integral derivative control. This is a controller. And a P&ID is a drawing. So this is a drawing that accompanies most processes that are chemical or flow oriented, and that kind of is in this chapter. It's kind of secondary in this chapter, but it is in this chapter. Okay, so you kind of have to, I'm going to go back and add a little bit more in this chapter with that. Okay, so we ended up in this area the other day, but I'm going to go down and I'm going to talk about P and ID drawings. So this is a listing of the type of things that you can have in a P and ID drawing. And these come from a organization called International Society of Automation, or ISA. They used to be called Instrument Society of America. And then they became International Society of Automation. And they have a lot of standards. We talked about one of them before, and that had to do with SP88. But we've kind of talked about them a little bit, but they also are big in the area of process. And they've defined they've kind of codified the symbols that are on a P and ID drawing. And when I handed that book around to you the other day, this is the kind of stuff that was on that drawing. And this typically is not a circle, it's called a bubble. And a bubble usually has in it, it has a top part and a bottom part, and I'll make it bigger so that I can describe what's in it. But the top part is the kind of device that it is, and the bottom part is an identifying number. So you'll see these circles on the drawings, and you saw those. If you looked at that book the other day, and you say, well, you didn't give me a chance to really go through and look at that book very much, I passed it around. If you want to look at it more, you can. But basically, tonight, what I want to talk to you about is looking at a P and ID and then translating that into a program, or looking at a process and translating that into a P and ID. So you look at a process and you translate that to a P and ID drawing. And then you look at that and you translate that into a program in your PLC. And I want to be able to go from here to here and from here to here tonight, if I can. In order to do that, you need to know what these letters mean. Okay? And there's a first digit, second digit, and sometimes a third digit, or third letter. They're letters, and they have meanings. Okay? And so some of them are listed in this table on page 81, 82, and 83 of my book. Okay? Now, also, I have another course that I teach, and in it, there is a set of slides. In those slides, this is the EET 4450 course. And in those slides, starting at about slide 59, and I'm going to put these in my text so that they're all in one spot, but right now they're not all. You get the idea that I've got things in multiple places, and I do. There's stuff here and there's stuff there, and I'm trying to. One of these days I'll get organized and put it all in one spot, but right now you're going to have to look in a couple places to get some definition on this, or you can just say ChatGPT it, and you can get the same information from ChatGPT. So it's kind of this is kind of universal information, but what I want you to get is, if I define a process, I want you to bring up the PNID and be able to do it, okay? And if I give you a PNID, I want you to be able to write a program. Simple, the beginning program, how about that? The very beginning program of how to create a program that will make that process actually run. And it isn't that hard. It gets hard when you add stuff, the subtleties. But the beginning program, just to get up and running, I want you to be able to go from the PNID to the program. Okay? And these two steps are what I want you to get out of this chapter. Okay? So, and you say, what is he going to ask on the next test? Well, this is part of it. This is part of what you will have to end up doing. Okay? So here are some PNIDs. Okay? So this is a PNID that's on one of those pictures, and anytime you see something IC, that means it's indicator controller, okay? So a bubble was something either IC or the other one is, there's two of them, something, and the other one, I'll get the other one in a minute. The RC. Okay, so this stands for indicator, and then the last word's for controller. This last one means a PID block in your PLC. Okay, this means a recorder, and this word means controller again, or PID. All right, so what do you think FIC stands for? What kind of thing would you think F would stand for? Flow. Okay. DIC, I haven't the foggiest idea what D stands for. I have no idea what this one stands for. Flow transmitter. That's what that guy stands for. And I don't know what PDT stands for. That means the third one's transmitter. PD means something, and then T stands for transmitter. Now, how am I going to figure this out? Go back to those sheets, page 80, 81, and 82, first letter, second letter, third letter, and you can figure this out. But the third letter is the key. Third letter with a C in it stands for a PID controller. Okay? What about this one? FIC. What does that mean? Flow indicator controller. What does FIC here mean? Flow indicator controller. Now here, you can look at it and you can see this one has an input and an output. There's no arrow going to this, but this is the flow transmitter, and it has to go this way, and then it goes from that way to the valve. So this one is just controlling the flow based on this flow transmitter to that valve. Everybody see that? What's the set point to this guy? If there's no second arrow going in, it has to be the what? The set point is from the faceplate. So this has a faceplate set point. What about this one? There's two arrows going in. This is an arrow going in even though it's not shown, and this is an arrow going in with the word set. That direct tip off that's a set point. So what does this process do? Especially with the idea that it says what, right? I think I was somewhere in that. Maybe it doesn't. Yeah, it does. It shows primary flow and secondary flow. What do you think this process does? Look at it and see if you can figure it out. What does it do? What does the multiplier stand for? A proportion, right? It's a constant. Everybody see that? It's a constant. If I put 1.5 in there, what do you think this flow would be with respect to this flow? 1.5. Does everybody see that? You don't see that the multiplier stand right there, which is basically a tip off that you're doing the multiplication of this flow times 1.5, and that becomes a set point for this one. So if this one was 50 gallons and your set point was one, and this multiplier was 1.5, this would be 75 gallons. Okay? So this is a ratio controller between the flow down the two pipes. Does everybody see that? Does everybody see how you can translate from a process to say, okay, what do I want? I have a pipe with a certain, I want to be able to set the flow, and then I have a second pipe that I want to set a ratio of the first pipe and the second pipe. And where did this little drawing come from? The LipTech book. I mean, this little vignettes of PID controllers, P and ID drawings. This is a P and ID drawing, by the way. This is a simple little P and ID drawing. Process instrumentation drawing. Right there it is. And now you are a little bit smarter at being able to look at a big drawing and see the parts and pieces, how to pick it apart. Does that make sense? Okay. What about this one? Oh my goodness. I gotta get this a little bigger. What is all this stuff? I don't really know, and I don't really care. I am a programmer of programming for this kind of stuff. A chemical engineer set this up, or some chemist or somebody 20, 30, 50 years ago, and all I am doing is setting it up in my plant to program to make it do the same thing, or try to do the same thing. Okay? So I take their PI. Okay, now this is bringing out this is getting a settling stage from what are they? They're reclaiming stuff here. They're reclaiming. I forget what it is, but this is a reclaiming. Okay, now look at this: continuous oxidation of cyanide waste with chlorine. Oh my goodness! Okay, how many of you want to work on this project? How many of you want to become, if you did get into this project, how many of you would like to be friends with the pipe fitters to make sure that they do a good job? Yeah, you want to make sure that the pipe fitters do an excellent job and they don't mess up, right? You don't want to have to walk into this thing and have chlorine gas spilling out around your shoes. You do not want that. This is not or cyanide gas coming out around your shoes. You do not want that in a situation, okay? But let's just pretend it doesn't say the word cyanide, and let's just say it says, maybe this is an ice cream plant or whatever. We're making ice cream. I don't really care what this is, but let's just say we don't really care what they're making, and take the word cyanide out and think cookies and cream, or cookies and cream ice cream, that type of thing. All right, so where are the PID controllers for this? Well, there's one there. There's one there. There's one there. There's one there. 1, 2, 3, 4. I count 4. Does anybody see any more? What's all this stuff over here? These are alarms. That's all they are. There's no third letter C, so they're not controllers. This is just alarms. Alarm element, alarm recorder, alarm signal low. And there's alarm or element alarm low, element high, and there's my alarm high. So all it is a low and a high alarm for this stuff. All it is. Analog value with a low and a high set point. Sounds alarms. Okay, enough on that. Here's some of the stuff having to do with how this actually works. I went too far. So here's some of these, how to build these. Okay, so here's a P and ID example, all right? So here's a process, and here is that process using a drawing. Okay, so here's the drawing for that process. So here's your physical process and then a drawing of that process. Okay? Usually they try to mimic the physical with a picture of it, some kind of picture of it. Okay, so here would be the physical vessel, and here is the pictorial on the P and ID. So you show valves as this kind of thing. You show vessels as something similar to the actual vessel. You show temperature recording controller. There it is right there, and the temperature transmitter right there. That's how you do it. Okay. Any questions about that? Here's my IC and RC. That's the tip off that's a controller. Now, each of the controllers have in them 3 major components. One, so if you are now looking at a bubble that says IC or RC, the translation of that into a programming block is this. There has to be a set point, there has to be a process variable, and there has to be a CV or output. Okay? The CV means control variable, or you can call it the output. I don't really care which. PV is process variable, SP is set point. You have to have those, and you have to have the name PID in there. So this is the rudiments of how to program a PID control block. You have to have those 3 components, okay? Now there's other things as well. but basically these are the ones that are common for all major controllers. And this is on slide 53 of the PowerPoint for EET 4450. So that's where this is located, okay? So you have to have these two going in and this going out. Now, these are physical controllers. These are single loop controllers, and the faceplate would be the thing on the front. You don't have to program that, you don't have to show that, but that's how that looks. And this is how you would do the setup if you were in Allen Bradley land. Okay, so Allen Bradley lets you play by doing a setup page that's free, that comes along with. If you program a PID block in either Allen Bradley or Siemens, so you power it, and then you have these two inputs, the process variable and the set point, and you have an output, okay? And you call this PID. PID, Ted. Up in the upper left-hand corner, there's one or two little things that you can click on, and this is the one that Allen Bradley has for the setup. So you can click on that with Allen Bradley, and then you get this page. It's a pop-up page that gives you all the ability to run that PID block from this page. Okay, so as you're setting up a PID block in the real world, you click in the upper right-hand corner, Allen Bradley or Siemens, and you get this, or something like this. This is the Allen Bradley version. Siemens has a little different look, but it's the same idea. Click in the upper right-hand corner, you get the ability to go into auto, to go into manual, to set it up. It's a setup page, okay? And then you get into these things, okay? That's how that's done, okay? Okay, now, let's go back to the back of the chapter 19. I want to go to chapter 19 in my texts because I want to pull it up. Okay, let's look at chapter 19. Look at it here. Now, in it, okay, so down here, I have a large number of these P and ID drawings. There's the one, there's another one, there's another one, there's another one. Now, these are all from prior tests that I've given, and this is case in point. This would be one where you could actually, there's a lot to this one. This is probably as good a one as you're going to find. And let's just get it and look at it for a minute. Right, so let's play with this one and see what we can come up with. So what would be the answer if I ask you to fill in all the, to give me a first cut program that would run this process? What would you end up with? How would you start? Find the controllers. Okay, that's the first step. Very good. Find all the controllers. Where are they? Well, there's a DIC, so let's just call that DIC. That's our first one. And we should give it a number. Like this is a PID block. Let's call it DIC 101, and that would be like 101 there. Okay? What about this one right here? What is that? FRC. And these can be stacked top to bottom. It's a PID, and it's an FRC 102. Okay, so this would be 102. And where else is there one? There's a FRC down here. This would be 103. And that would be 103. And what about over here? There is a TRC and another TRC, so we can put them over here, I guess. That's fine. TRC, this would be 104, and this would be 105. This would be TRC 104 and TRC 105. Okay? Now, what must they have in them? They must have 2 inputs and 1 output. So we put those in, and we don't necessarily label them yet, but we just acknowledge that there's that. Okay? Now we go back and we say, where is this coming from and where is this signal coming from? So where would be the set point for this DIC? There is no second arrow in, so it's going to come from the set point from HMI. So you have to set the set point for this guy from the HMI. The signal that is coming to it from its PV is the FY 101. This is FY 101. That's my feedback signal. So no, it's not. I'm sorry. That's not the feedback. The signal is coming from. The signal is coming from TRC 105. So that's wrong. So this one, they can get hard. This one is. So this one, the arrow here is coming from down here, and it's coming from TRC 105. So the PV is from TRC 105. And what is my output going to? It's going to this FRC set point. So it's going to FRC 102 set point. Does everybody see that? The output is going to the set point for this controller right here. So let's go down to FRC 102. What's its set point? Say again? That's okay, this is, the arrow here is coming from all the way down here. It's from the TRC 105. That's where this is going. And then it goes both this way and this way. So you see it, the arrow pointing down and pointing to there. So this arrow is the one that's going up there. It's going to there. This guy is important. He's feeding the PV up here. He's feeding this valve, or this guy right here. That's a valve, flow controller valve, and he's also flow output for something, and I don't know exactly what it's doing. But anyway, this guy right down here is feeding this way and this way. And he controls that valve, and he controls this thing, whatever this thing is. I really don't know. Okay? But I do know that the set point of this is not coming from any device, because there's an arrow going in and an arrow going out. You need two arrows going in for there to be a set point. When they don't label either arrow, either one coming in, you have to kind of be a detective to figure out which one is which. And you go back and you ask the person that generated this, if you're the programmer, which one is which. But there has to be two, or if there's only one, the other one comes from the HMI. Okay? Everybody get this is a puzzle. But you can create from these puzzles, you can actually create the program. And that's what I'm asking it to be able to do. There's two inputs and one output. Every one of them has two inputs and one output. So the DIC is coming from down here. Now, this FRC has a set point from the DIC CV, or the output. The CV is the output, okay? I could say this is the CV, or I can say it's the output. And I'm just saying the DIC CV, all right? Or I could say DIC, I should say DIC 101 CV, or output. What is the PV for this guy? Well, it's coming from this thing right here, and usually you label the FT, which is the flow transmitter, as 102, the same number as the controller. So this would be, the PV is FT 102. So this would be labeled the same as that number right there. And then you multiply that, and then you bring down to this one. So this is a feed A and a feed B, and this is doing the same thing. This is a ratio, and this would be my watt. This would be my set point for FRC 103. My set point would be FT 102 times, my set point here would be FT 102 times a number, which would be that number right there. And that's my set point, and in my process variable is FT 103. And my output is to a valve, and that's just, that does just say a valve. And this one up here is to the output of this one is to, that's the, the output of this one also goes to a valve. Let's just call it a valve. Usually there's a number with that valve, but anyway. This is a ratio setting device where this is an output, and this is a ratio of that output based on that number right there. So these are two feeds coming in at a ratio, and that's my ratio right there. Okay? Now, what about these TRCs over here? Okay? This one has no second input, so it's a set point. This is from the set point is from the HMI. And this output from this one, and the other PV is from TT 104, and the output is to a set point to TRC 105, and the set point for PID 105 is the TRC 104 CV, the output. That's my set point. That's that number right there. That's my other number in here. It's TT 105. My PV is TT 105, and my output goes to that valve down there, which is a valve, and also the input, the PV to DIC 101. And I'm done. You say, is that all it is? That's my program. I take that, put it in my programmable controller, hit run, and I get my first shot at making this process run. Now you say, is that all there is to it? No, that's not all there is, and you know that, right? But this is how you get started running a program for a process. You run this, and then you start adding things, okay? But this is a first shot at doing that. Now, okay? Now, what else is there? Well, there's a lot more. And I will go back and I'll show you little pieces of it here in a minute, okay? So, war story time, right? So, this is a steel furnace, a reheat furnace for steel, okay? And they heat the steel up on rollers in this device. This is commonly referred to as a shake and bake. All right? If your mom has ever made shake and bake, you can identify with that, okay? But it's commonly referred to as a shake and bake. In this furnace, you have rollers. And the steel rides on these rollers, and they can be more than one piece of steel in there, or they can just be one piece in there. But the rollers constantly are going back and forth and back and forth and back and forth and back and forth. Why do they do that? What are the rollers made of? Steel. What would happen if the rollers ever stopped rolling? They would sag, they would bend. And if they bent, they're done, they're ruined. So this process is twofold. You have to provide heat at a control level, and you have to make sure that the rollers are constantly going back and forth and back and forth, okay? Now, in this process, your temperature does not have to go above the temperature that gas will automatically burn off, all right? So if you have, there's a temperature, and I don't know exactly what it is, in the 700 range in Celsius. If you have the temperature less than that, the natural gas will not burn off if you have an excess of gas. The ratio of gas to air is 9.1 to 1 or thereabouts. Okay, so you have 9.1 parts air and 1 part gas. That's natural gas to get heat. If you provide 9.2, you're good. You're not quite on target, but you're okay. If you do 9.0 to 1, you pool gas. Does everybody understand that? You pool gas. And what happens if it pools less than the burning temperature, the burn off temperature of natural gas? The big boom, it booms. It actually explodes in there. So you have to keep it at 9.1 or a little higher. You want to keep it as close to 9.1 as possible. But the question comes up, what happens when you change the set point? In other words, if you start to move the set point, what happens? Okay? And I was asked to program this, and I did not have a P and ID. I just had a description that some people had written down, and they kept using the word, well, it's cost limiting. I had no, how many of you know what the word cross limiting means? If you said in a process, it means cross-limiting. How many of you have any clue as to what that means? No, most of you don't have a clue, right? All right, but I got that book. These guys had no idea. They hired me, and I had no idea. It was a very bad position to be in. So I knew that this book existed, and I went ahead and bought it myself. And what did I do? Opened it up, went to the index, did what? Look for the word cross-limiting. Fortunately for me, it's in there. Okay? And this was the picture basically that I got from cross-limiting, okay? I took it to the process guy, who was the head guy, and I said, "Is this what you want?" And he said, "Yes, that's exactly what I want." So from not being able to program it to being able to look at a picture and program it was one picture, and it was well worth the effort to buy that book for that reason. But I that's what I did. And it basically allowed me to write the program to be able to do that. Now, what does this mean? What does this mean? It means when you're increasing, you want to increase which first. There's a lag block in there. Everybody understand what a lag block does? Any ideas what a lag block does? It lags. The signal lags by 5 or 7 or 10 seconds. So one of them is going up, and then the other one lags before it starts to go up. Now, which one do you want to go up first? If you're getting, do you want to pour more gas in than the 1 to 9.1? No, you want the air to go first. You want to keep more air, and then you want to lag, and then after 5 or 10 seconds, you want to bring the gas up. Okay? Now, if you're going down, which one do you want to move first? How many of you want to move the air first? How many of you want to move the gas first? When you're going down, move the gas first when you're going down, move the air first when you're going up. That's what lag means. That's what cross-limiting means. Does that make sense? Can you write this in your PLC? The answer is yes. I did it. You can do it as well. But without that picture, without a picture like that, you have no clue. But with that picture, you follow me? You can write that program. Now, how would you write a lag block if there is no lag block physically in there? How would you create a lag block? Yes, sir. You have an idea? Okay, some programmable controllers actually have a lag block, or you might be able to find one. Somebody has some kind of a ChatGPT or whatever. I don't know, but how would you build a lag block if you don't physically have a lag block? How about a FIFO stack that just goes out the bottom? Does everybody follow that? So you start putting numbers in, and every time you put a number in, you keep moving them down. Every 10th of a second, you keep moving it down. So after 50 moves, you have what? 5 seconds. So basically, a FIFO stack where you just keep moving them down is a lag block. Believe it or not, that's exactly how I built mine. Okay, just keep moving them down, and after, and if you want to go to 55, that's 5.5 seconds. So every 10th of a second, you just keep moving it down. That was easy. Okay, now that is how you build a controller in a where the temperature is less than the ignition temperature of natural gas. Now this is for a glass furnace or a furnace where you're running above that temperature, okay? Where you're running above that and you're burning it off, okay? Now what is this about? What are we doing here? We're taking a thermocouple and bringing it into the temperature controller. The output of the temperature controller is feeding the gas and the oxygen or the air. You can do either one. And then those are actually controlling the valves. Does everybody see that this is how you would control a zone of a glass furnace or a steel furnace that you want to have heated up to a certain value without this idea of cross-limiting? Because that's how you do it, right there. okay? How many of you think now with what we just talked about, you could actually do that? Probably could, okay? That's all it is per zone, and how many zones do you have? Basically, it determines how many of these setups you actually have to have. That's it. Now, the key to this is what is the units of the output of the temperature controller? That's a good question. It's usually BTUs or BTUs per hour or BTUs per minute, but it's in BTUs. The output is in BTUs. So again, this is not all simple. There's chemistry involved, there's physical things involved, but basically what you just have here is how to build a glass or steel furnace control. Right there it is. I've done 2 of these and they all work the same way. And then I've done 2 of the steel furnaces and they work the same way, except that the one steel furnace had the blow and it had the cross limiting in it and all that kind of stuff. So again, you can, now the cross limiting one has this extra because why? You have to bring the temperature down when you're hardening steel. Now if you're just making it hot, you go high, but if you are, whatever, it's a, okay, now I'm going to come back here and I'm going to talk about another process here in a minute. And I want to show you what, okay, so this is that same furnace. And I want to talk to you just a second about that stack damper up there. So basically every furnace has a pressure sensor and a PID based on pressure. So what does this thing do? So basically you have a pressure sensor, analog pressure sensor, and a stack damper. So you're putting gas and air in, and because you're putting something in, something has to go out. But you don't want to put any more out than you absolutely have to. Why? Because that's heat. You're extracting heat, and you don't lose heat if you don't have to. But you have to take some of it out because why? It'll get bigger and bigger and whatever, it'll blow up. So you have to be able to control the pressure in the furnace. So you have a fan up above that's pulling the air out, and you have a stack damper on that fan, okay? Now, that's a slow process. It's a slow-moving PID algorithm. But what happens when you open the door? It goes like this. The process starts to oscillate, and you get flames all over the place. And as a matter of fact, the first time we opened the door with that process going like that, it burned the door up, okay? We replaced it really quickly and all that kind of stuff, but you don't want to, every time you open the door, you have to replace the door. So what do? Well, this is where it gets interesting because I had no clue. I'm just the programmer, right? We burned up the door. They had to replace the door. The guy told me, he says, what you got to do, this is the kind of thing where you get into a plant and you start working with people, and there's somebody in that plant that knows all the secrets. And this was the guy, and he was telling me what to do. He said, what you do is you go from auto to manual, add 2%, and then go back to auto. I said, what? He just grinned and said, do it. And I did. It took me about 10 minutes to program that little change, and I did, and it worked perfectly. Now, what did we actually do? We basically went to manual, stuck it, and added 2% to the output and put it back in auto, because he knew that 2%, if you're running at 60% or whatever, and it went to 62%, it would balance out and be okay. And it did, and it worked fantastic. Okay, that solved that problem. But I'm going to tell you another one that it wasn't so good. And this is having to do with my PhD. Okay, so they call me doctor because I did a PhD in industrial engineering at the University of Toledo. And my project was to find out of 200 variables over at the plant, the LOF plant behind Hollywood Casino, there was a problem with bubbles in the glass, okay? And the variable that caused the problem was the stack damper pressure. Now you say, that's interesting. It was the same problem. Yes, it was. It was the same exact problem. But that caused bubbles in the glass. And now I didn't find this problem in time to actually help them. They fired the guy, and I'm sorry that that happened, but it happened. But out of the 200 variables, that was the problem. That was the one. But we found it, but we didn't find it in time. They had fired the guy, and a guy came over from Britain. And you know what he probably did? Nobody would tell anybody what he did. But I bet he did the same thing. You stick the output, add a little bit, turn it back to auto, and it'll turn on and it'll work. So basically, when stuff starts to oscillate, sometimes what do? You stick it in manual, and then you do something with it. You either hold it in manual, or like what we did was add 2%, and you're good to go. That's why they call me a doctor. That right there, except it was for the glass plant. Okay, that's that. Now I want to show you what I want you to do. You're probably going to shoot me, but I want you to create a P&ID for a process, and this is a process. This is a simple process, but it's a process nonetheless, and it's in. And this is again it's in the labs for 4450, and I kind of apologize for doing this way, but I'm gonna probably give it to you over the weekend and write it up and have it ready. But it's lab number 7, and we've tried this and we have problems with it, so don't try to do this with but I want you to try to write a P&ID for this process. It's lab number 7 of this, and I'm going to show it to you what it actually does. Okay, so here is the process. So here is the level loop. Let me show you what this looks like. I'll physically show you what it looks like. Okay, somewhere in here there's a picture, maybe not. Maybe there's no picture in this one. Yeah, there's a picture right there. So here is the side view of it. So there's an upper tank and a lower tank, and you can't really see it very well, but there's a pump down here in the bottom that pumps the liquid back up, and it goes through this flow valve, and then it goes to the top, and then it dumps back down in, and then there's up here there is a sensor that senses the height. So the outer loop is the level, and the inner loop is the flow. So that's all I'm going to really tell you, except I'm going to show you this picture. And from that, you can pretty well write the P&ID. And you don't have to do too much more than that. But here are the two P&ID. Here's the two PID blocks. Okay? So the output of the level block is the input to the flow block. Right there it is. But here is the picture of this. And here's the outer one. This is the level block. Okay, this is the level, and this is the flow. So if you control the outer loop, basically to a set point, I want to go to 50% or 75% or whatever, then it tries to go there based on the fact that you have output valves that you can control and all that kind of stuff. And then they say, give me more or less, and then that gives me my flow, and then my flow is a PID block based on a pump and a flow valve. So the flow valve is the PV, and the set point of this guy is the output of this guy. All right? Does that make sense? Because that's exactly what it is. Now I want you to create a P&ID of this. Okay? Now that may sound ridiculous, but that's what I'm going to hit you with on tomorrow or Friday or whatever. That's what I'm going to ask you to try to do. So create a P&ID of this process. Okay, enough on that, but that's what that is. There's a picture of this in the there's a picture of this in here somewhere. Somewhere in here, there's a picture of this guy. Let me see if I can find it. Yeah, there's the sensor, and there's the pump, and there's a picture of it right there. Okay, the sensor, the flow, the pump, the flow meter. There's the flow meter, and you control the flow with the pump from the output of the PLC. There it is. There's a picture. 19-24 is the picture of this. So it'll be picture, a little bit of description, and I want a P and ID of this process. Okay, and I know everybody's going to come up with a little bit different. Here, I want you to have to, in your time here, come up with the P and ID based on the bubbles and based on the PowerPoints and based on the symbols on page 80, 81, and 82, and give them numbers, and you will have created your first P and ID. Okay? The other problem there's really three basic problems in this chapter that I want you to be able to do. The second one is the one that I showed you where we actually did the 5 PIDs and that type of thing. And we'll probably give you that assignment next week. But this is the first one I want you to be able to do, is this one right here. Okay? Any questions anybody has? Simple. Hand drawing is fine. If you do a hand drawing, make it neat. If you do it with Visio works really, really well. Other than that, have at it. Okay? Yes, sir.
You say you were going to send out one.
There'll be an email. Yes, this will come out in an email, and I'll show you. I'll state in there these pictures and all that stuff. So it'll be organized. In other words, it won't just be fly by the seat of your pants. Here's the pictures. Here's what I want. Here's how I want to do it. It's based on this picture right here. Any questions anybody has? Now, can you go out today after tonight and write a steel reheat furnace program or a glass furnace heat up program? I tell you this much. One person did. Not many have done it, but one person went right out on his own after studying chapter 19 and wrote a steel reheat furnace for the same company that I've written the original one for. He looked at my program, but basically he went out and wrote it from scratch, and it worked on a reheat furnace. And if you don't believe him, or if you don't believe me, go up to Algoma Steel in Sault Ste. Marie, Canada, and ask them, did I not write one? And this other guy came along and write one after me, and he did. He wrote it right out of this. He got the ideas from this chapter. He looked at it, looked at the program that I'd written, and wrote it again, and it worked. It ain't that hard, but you may not believe me, but this is a whole different arena than what you probably. How many of you thought that you might even possibly touch on this subject at all? How many of you thought this course was about anything like this? Controlling the heat in a furnace. It's scary, right? It is. But it's very doable. This is all this is, right there. The keys of the kingdom are right in this chapter. Because I've written 2 glass furnaces and 2 steel furnaces. They're the same thing. The only thing you got to ask them is, do you want that converted to standard temperature and pressure? You ask that on every single variable coming in. You want that converted to standard temperature and pressure? And they'll either say yes or no, and then you're in. All right? Can you do that? Yeah, you can convert to standard temperature and pressure. It's not hard. All right? Take care. See you.